Okay, sorry for the problem. Today I will introduce a paper, the title Audio-Driven Neural Gesture Reenactment with Video Motion Graphs. This paper is presented in CVPR last year, and as you can see in the figure, the paper produced a system for generating a new video by cutting and reassembling, blending clips from an input reference video. You know, one of my research field is video editing, specifically taking video as an input and generating another interesting form of video by utilizing the input frames. So I thought this paper was quite similar to my previous paper, Pop Stage, for auto generation of stage mix video, both in ideas as well as in method approach for solving the problem. Yeah, that's why I picked this paper for this seminar and want to share with you guys because many of you love my paper. Okay. Let's go on to the introduction. Gestures enhances the expressiveness and can help audience to better comprehend the speech content. And demands for techniques to create plausible gesture videos has been increasing. Especially these days in the area of metaverse, this kind of synthesizing techniques are even more important issue. The technique can be used in many applications such as digital voice assistance and also photorealistic virtual avatars. Yeah. Previous studies on gesture video synthesis show low quality results. There are lots of noticeable artifacts in the resulting video, also with the low video resolution. This is because the previous study dissected the problem into two independent models, like the first stage predict the gesture pose from the audio input, and then as a second stage generate the reenacted gestures video based on the predicted pose. So in this paper, the goal is to generate high-resolution, high-quality speech gesture videos with low artifacts and low ghosting effect by reassembling the video segments from the reference input video. And they assume a speech video as an input with somewhat static camera and also non-dynamic human movement. Here's the overview of the proposed video reenactment method. The first step of the method creates video motion graph here for splitting and reassembling the video input video frames. Then, when the target speech audio for reenactment comes in, they process finding and this editing path in the graph according to the audio information is performed. And direct playback on the searched path like this way may cause temporary inconsistency at the transitioning frames. So the last part is the blending steps to make this transitioning video visually seamlessly. By going through these three steps in turns, video motion graph construction, audio research, pose-aware video blending, the gesture is reenacted according to the target audio is obtained. Okay, so I will show the result first. So yeah, here's the reference video of speaker A. Can you hear the sound? No. I think I have problem with Zoom, so I will share the this project, link up the project page. Yeah. So the reference input is two. The first is the reference video of speaker A, and also another one is target audio, only audio from speaker B, and the output is the reenacted video, A's appearances with B's voice, like this way. You can check it individually. Okay, go back to the presentation. 좋아. Yeah, contributions of the paper is as follows. First contribution is related to the idea and overall framework, a new system that creates high-quality human speech video with realistic gesture driven by audio only, and the others are related to the method part, a video motion graph and audio-based search algorithm, and the last one is a pose-aware video blending neural network. Let's dig into the method part. Yeah, methods for the first part, video motion graph construction. The goal of this part is to formulate the path planning problem with the graph structure consists of nodes and edges. Each node represents the frame index and corresponding audio features. And I will talk about this audio features later part. And the directed edges indicate the transition between two frames. You can see the black line here, here, like this. In graph indicates the original natural transition in the input reference video. Then to expand the graph connectivity and enable non-linear video playback, synthetic transition presented in purple line here, this are introduced. This is called synthetic transitions in this paper. And these synthetic transitions are created based on the similarity of the speaker's pose in the reference video frames between these two nodes. And for the similarity, they calculate two dissimilarity values. They compute 3D space pose dissimilarity for each pairs of frames M and N based on the Euclidean distance of pose parameters extracted from SMPR model. So yeah, calculate this 3D space pose dissimilarity, and then they calculate the image space pose dissimilarity by using the previous method here. Representing the mesh surface area on the image space. So using this mesh surface area information, this similarity is estimated by intersection of union between two pairs of frames. Then if these two dissimilarity values are lower than the set threshold, synthetic transition edges are created like this way. Then move on to the second part to find the editing path on the graph that follows the target audio. First, they split the audio into word level clips and check if the split videos are in the presented keywords, like in this table. These keywords were created by authors. They said this is a dictionary of common words that are frequently used for gestures. And then editing path is obtained by beam search algorithm, taking into account whether the keywords between the audio in reference video and the target audio match, and also consider the previously calculated transition cost and clip duration cost. Actually, I didn't fully understand this part because there seems to be missing details in description, and also I don't play with the audio domain. So I think if you're interested in this part, please refer to the paper or discuss with me later time.
Yes, so
I guess
question here. Yes, clip duration cost. That means if the duration is long, then you have like a more higher distance. So that means it will increase the very fast transition with the short duration.
oh no, that's not related to the duration, like not related to the synthetic transition duration for the synthetic transition. It's like check the duration of the original clip, you know, the word duration of check the similarity of the duration between the reference video audio and the another input audio. You get it?
No, yeah, okay, so transition cost will, okay, be determined by the distance between 3D feature and then 2D image domain distance, and then clip duration cost.
And
yes,
then
so,
clip
yeah,
duration.
so clip duration cost means, so if the duration is long, then it will not allow the transition, right? Is that correct? Am I missing something?
No, I mean, I will give an examples like if you say the word love in very long duration, like love, and another clip says like love in very short duration, love, then compare this similarity, like the duration of the word.
Okay, okay, duration of the word.
Yeah, not for the transition.
Okay.
Yeah, so I get this part is not to be a, it doesn't seem to be a technical part because the beam search is quite simple algorithm, and there seem to be tricky things in setting, handling, reversing, forcing the transition. So yeah, please refer to the paper talk later time.
So I have a question before moving on. So is the previous slide or actually a method for constructing the motion graph, or is it for the transition? So I think the first method one, seems to be constructing the motion graph, right? And is the second one also constructing a motion graph based on the clip, like the audio?
Oh no, actually in the first part of method, video motion graph construction, the node has the audio features already. So this is for the just for the construct the graph. And then the second part is finding the optimal editing path by like searching the line that follows to the target audio.
When you construct the motion graph, you will consider the distance between frames based on the distance defined by this 2D feature and 3D image.
Yeah, but that is only for the creating the synthetic transition, these edges, not for the like obtain the editing paths. Just for like making possible transitions, all the
Yes.
possible
Yeah, so
transitions.
that's the construction of motion graph, right?
Mm-hmm.
Yeah, so when you construct the motion graph, you will see if the frames are close enough to be transitioned or not, based on the definition of the distances.
Yeah.
Yeah. Okay. Yeah. So you will use for that 3D distance information and 2D distance information.
Yes, right.
Okay.
So is the method 2 is for finding the path given a different audio clip?
Yes, right.
Oh, okay, thank you.
Okay. And this is the final part, generating the pulse-aware blended frames for smooth clip transition. And for the smooth transition, they use ARPA blending like this black line and figure. And this is a pulse-aware blending network. The goal of the network is to generate a blended frame T from input frames I and another input frame J with blended weight ARPA. The network consists of two parallel streams for ARPA blending. Here, make frame T similar to the input frame I, and another stream is for make frame T similar to input frame J. The first stage is for warping body image features based on the SMPR pulse parameters. So as an input, RGB image, foreground mask, and SMPR pulse parameters are used as an input to the network, and through this spatial encoder can get the deep feature. And using the initial mesh flow and deep feature as an input, mesh flow estimator estimates the mesh flow for the warping here. And for basically the mesh flow is computed by vector distances following these steps. First, calculate 3D SMPR pulse parameters for the target blended frame T, like similar to the ARPA blending, to get this pulse parameter theta, and project these 3D SMPR parameters to the image space vector B, and calculate the vector displacement like this way. Because the first stage is based on the SMPR pulse parameters, the result image ignores details such as textures on clothing, and also may have ghosting effects. So the second stage is for refining the warping by computing the residual optical flow. By using the off-the-shelf frame interpolation network based on the optical flow, they warp the image again. And this process is also performed for another input image J. And the final output image is generated through the alpha blending of these two representations. Authors trained the network using the reference video frames, like sample triplet of frame images in the reference videos. Given a target frame T, other input could be selected by randomly closed frames like T-4 and T+3 frames like this way. And they design the laws to promote better flow estimation and finer frame reconstruction. For the image reconstruction, they use L1 reconstruction laws and use perceptron laws using VGG19, and also another reconstruction laws directed from the rapid representations. And not other terms is for mesh warping and optical flow and smoothness for them. This is the end of the method. For evaluation, they compare the blending network with previous method, like frame interpolation method and pix-to-pix backbone method. And the results show that numerically better results, as you seen in the here table. They also do the evaluation study by excluding the mesh flow stage and optical flow stage, respectively. And for qualitatively evaluation, they perform the user study among the ground truth video, like B's appearance with B's voice, and ours full, A's appearance with B's voice, and ours no search, which randomly takes the editing passes. Two of them were presented to the users, and user is guided to select one of them, pick the better one. Gesture reenactment was the paper's goal, so the face in the video was covered by white box like this way. And they demonstrate the quality of the audio-based searching algorithm through the last part, comparing ours full and ours no search. And for the ground truth, they obtained a high result of like 41%. Limitations. Authors use a predefined small number of keywords, so it may fail on other vocabularies. And also, because the proposed blending network can blend the foreground human poses and slight background changes, so it can fail and dramatically change its backgrounds like this video. Here. You can see the artifact and it goes back here. And last one is not a limitation, but I tag it because it was interesting to present the application concern of this method. They said like this offers the ability of creating fake videos for malicious purposes. So, and also said like detecting deepfakes video is an active area of research. This is end of the paper, end of the presentation. Do you have any questions?
Is the system retrained for every new reference video, or once it's trained with one reference video, then it can be used for different audio?
They have to retrain network per the reference video.
Okay. And another related question is, yeah, so you show the result of one trained reference video driven by different person's audio, right? But
Yeah, right.
If the different person's audio is, like, for instance, because of the gender difference and because the way people speak different, because of the like a pitch difference, all this, is it still like possible to drive another person's the video with different person's audio?
I think it doesn't matter because actually the goal of the paper is to like generating only the gesture, handling only the gesture part. So no matter
So
gender.
when it is trained, somehow audio feature is reflected to the system during the training, right? So for this particular audio input, the corresponding gesture video will be generated.
Yeah.
And I was wondering, like, because of the gender difference, because of the way the people speak different, possibly like pitch will be different from person to person and so on. So how accurate, I was wondering how accurately the system will be driven by different person's voice.
Well, I think as I say before, like this is the I think Professor you mentioned about the facial expression part, not the gesture.
Gesture, I mean gesture, not facial.
Gesture?
Yeah. Yeah, but then gesture, when gesture is generated, will it be somehow corresponding to the audio input, right?
Oh, yes, right.
Yeah, so audio input will be trained for this particular person. For instance, this male person's audio. Then now,
Yeah.
yeah, the female person's audio is now input.
Yeah. Actually, the result is audio. If the speaker is same and the inputs like in the reference video was used from speaker A and target audio from speaker A is shows the better quality, like they share the same like gesture or speech from this audio speech, but you know, I think this second result is, I remember, the reference video is woman and the target audio was man, I think, but the result is plausible. So yeah,
So is the target audio different identity from the source audio, or does it have to be the same?
it doesn't matter.
It doesn't
You
matter.
can use the use a different speaker, but can get a better result with using the same speaker in the reference video.
Okay.
I also had a suggestion, because as a human, when we talk, our hand gestures are not constant. Sometimes I might use another hand gesture when I'm telling a sentence. For the same sentence, I might use a little bit different hand gesture. In this kind of scenarios, that for one input, you have different possible outputs, usually people use mixture of expert or gating networks. So when it generates the output, it will generate 2-3 versions or multiple versions of the hand gesture for a given audio. It might be more realistic to the scenario. You know, where is the problem if we don't do that? For example, in one training video, my hand gesture is like this. In the other one, for the same audio, it might be a little bit different. So network will confuse. But when you use mixture of expert or gating networks, it will consider different conditions. So it will be one-to-many mapping function instead of one-to-one mapping function. And I think they didn't use mixture of expert or gating networks in this literature. It might be an interesting future research. Thank you.
That's a good idea. And I think in this method, they use beam search algorithm to find the optimal path. So I think they can later consider the variation of the same word, same audio signal, but I'm not sure this part. Yeah, good idea. Thank you. Another. Okay, I will finish my presentation. Thank you for listening.